So let's look now at rational functions, and we're going to look at a couple new topics here. We're going to first determine vertical and horizontal asymptotes, which might be new to you, find intercepts, we've done that before with other function, and then determine any holes in a rational function. But first, let's define a rational function, and a rational function is really just a fraction. Rational function of f of x is just g of x over h of x. And remember, the denominator, h of x, cannot be equal to 0. So whatever this function is in the bottom, it can't equal 0. So here's an example. We have some linear function over some quadratic function, creating a fraction, creating a rational function. An asymptote, then, is either a vertical or horizontal line that a graph approaches but never actually touches. And this idea of a horizontal or vertical line is one of the keys to graphing a rational function, a value that it gets close to but never actually touches. So let's look at a basic rational function, and we're going to start by doing this with a table of values, and from this table of values we'll get a picture, and then we'll figure out a way to do this much easier. So when we have our table of values, we want to pick any x value that makes the math easy, and we can put that into our function. Well, first of all, we can see that in the denominator here, x cannot equal 1. We can never put x equals 1 into that denominator. So we're going to choose values that are not 1, but do make the math pretty easy. So let's put 0 into that function. When we put 0 in there, we're going to get 5 over 0 minus 1, which is really just negative 5. If we were to put negative 1 in there, negative 1 minus 1 is negative 2. We'd be at negative 5 over 2. If we were to put negative 4 in there, again, trying to choose some values that make the math easy, negative 4 minus 1 is negative 5. 5 over negative 5 is negative 1. We can also choose some positive values. And some of these positive values that make the math easy, well, let's put 2 in here. 2 into that value, the denominator becomes 2 minus 1, which is 1, and of course we would just end up with 5. If we put 6 in there, 6 minus 1 is 5. 5 over 5 is going to give us 1. And let's put a value for 3, let's say. Still pretty easy to do the math there. 5 over 3 minus 1, 5 over 2. And we're going to use these points to graph our function. So take a second now on your own graph and plot all those points. So there's our points plotted, and we could draw a sketch from here, but I do want to do 2 additional points. And these might seem like weird x values, but I want to choose x equals 1/2 and put that into our function. If we put that into our function, the math is a little bit trickier, but we get 5 over 1/2 minus 1, which is really just 5 over negative 1/2. And remember, when we divide by negative 1/2, it's the same as multiplying by 2, which is really just negative 10. So at 1/2 on our graph, we're down here at negative 10. Now I'm also going to choose another point that's a fraction, 3 over 2. And you're going to see pretty quick here why we choose those values. If we do that in math again, this time we're going to get positive 10. And we're going to be way up here at positive 10 for y. And now what we can see is we see that here is our sketch. There's values like so that connect, and like so. And what we can see is that our graph never actually touches x equals 1. That's where we would have an asymptote. And we would sketch in our asymptote with a dotted line, like so. There is our vertical asymptote. Now there's also a horizontal asymptote. If we look at this graph, they get closer and closer to that value of y equals 0. There is our horizontal and our vertical asymptotes. And if we look at our original function, there is no number we can put into here to get that equal to 0. That's why y equals 0 is an asymptote. And also, x can't equal 1, so that creates an asymptote. And there is our basic rational function approaching two asymptotes, which they will never cross. So we want to use this now and try and figure out how can we get to this graph without doing a table of values. And the first thing we want to do is actually determine the asymptotes. And the vertical asymptotes, much like the example we just did, come from the restrictions in the denominator. So here's our formal definition. F of x equals g of x over h of x. And if there is some value c that is a 0 in h of x, the denominator, then the line x equals c is the vertical asymptote. And we're going to use this to find vertical asymptotes of rational functions. So let's look at this example. Here's our function f of x. We want to find any zeros that exist in the denominator. And we did this all in the last chapter, finding the zeros. Well, we'll just take our function, and we're not going to worry about the numerator. All we have to do is find the zeros of the denominator. And we can find those zeros by factoring. There's our denominator in factored form, but we have to go one step further because we have a difference of squares in the denominator, which becomes x minus 3 and x plus 3. Now that it's in fully factored form, our zeros are x equals 0, x equals negative 3, and x equals 3. And these zeros in the denominator are actually our vertical asymptotes. And that's how we determine the vertical asymptotes of any function. Now, not every function will have a vertical asymptote, and it could have multiple vertical asymptotes, but that's how we would determine the zeros that are in the denominator. Well, what about the horizontal asymptotes? And the horizontal asymptotes are a little bit different here. To determine the horizontal asymptotes, we're going to examine the end behavior as x approaches infinity, gets really, really big. And this is a concept you'll use in calculus as well. And I just want to explain for a second what this means. So let's imagine we have a rational function 1 over x. If we let x get closer to infinity, get bigger and bigger, let's see what happens to our values. So our first one, let's let x equal 10. Of course, that would be just 1/10, which is 0.1. If we made x even bigger, let's say it's 100, we'll get 1 over 100, and we'll get 0.01. Well, let's make x even bigger, 1,000. And you can probably already see a pattern occurring here. Our value is getting smaller and smaller. And as x gets really, really big, we're going to have a really big number in the denominator. Some really big infinite number in the denominator. And what we say is that's going to be a whole lot of zeros, which is really just approximately 0. And we're going to use that approximation. And this is also something we do in calculus quite a bit. As x gets really, really big, any fraction with a denominator of x will get closer and closer to 0. So we're going to use that idea to determine the horizontal asymptotes. And to determine the horizontal asymptotes, what we do is we divide every power of x by the highest power of x, and then set x to infinity. Now that might seem a little confusing at first, but we're going to do an example and explain what that means. Because what this is going to do is allow everything but our leading terms to disappear, And we have to be careful of constants if they exist, because they're going to have to be determined in the horizontal asymptote. And all of this is going to become clearer as we work our way through these next three examples. So here's our function, the same function that we did before. We want to determine the horizontal asymptotes. So what we're going to do is take our function and look for the highest power of x. Highest power of x in this case is x cubed. So we're going to take every term and divide by x cubed. And what this allows us to do is find the horizontal asymptote. Everything by x cubed. And then we're going to simplify each term individually. So the first term, 2x over x cubed, is going to become 2 over x squared minus, there's no simplification on this term, 5 over x cubed. X cubed over x cubed is 1, and then we get 9 over x, like so. Now we use the power of infinity. Now we let x get really, really big, approaching infinity. And as it approaches infinity, anything with x in the denominator will get closer and closer to 0. So that'll approach 0. This will approach 0. And this will approach 0. And all we're left with, and this is an approximate because we are approaching infinity, we'll have 0 minus 0 over 1 minus 0, which is really 0 over 1, which is just 0. So that tells us that our horizontal asymptote is at y equals that number. That's a simple way to find the horizontal asymptote. So let's try another. Here's one that's a little more complex, but we still do the same thing. Take every term and divide it by the highest power of x. Remember, if we have a fraction and we do everything to each term, it's not going to change our overall solution. And after you do a few of these, you're probably going to get much better at them and see a pattern just in the original polynomial. So there it is, dividing everything by x squared. So if we were to simplify this down, we would get 6 plus 2 over x minus 1 over x squared all over 4 minus 9 over x plus 7 over x squared. And at this point, now we set x to infinity, make x really, really big. And all of these terms that have x's in the denominator will all approach 0. They get closer and closer to 0. And what we're left with is just 6 over 4, which of course is 3 over 2. And this is then our asymptote. So we can say that our horizontal asymptote is at y equals 3 halves. And there's our horizontal asymptote. So pretty easy to do. Just divide by the highest power. See if you can do this one on your own. So if we divide everything by the highest power, which would be x squared, and then simplify it down, there's our solution we get. So now we let x get really, really big. This will become 0, this will become 0, and this will become 0. And what we're left with then is 3 over 0 minus 3. But now here's the problem. 3 over 0 does not exist. So if we get a solution that does not exist, then we can say there's no horizontal asymptote. And we have to be very careful over that. 3 over 0 does not exist. It doesn't matter that we have some other value over here, there's no horizontal asymptote. If it did exist, we would take that number and minus 3 to determine the horizontal asymptote. We would bring that constant along. And we're going to do this a lot throughout this course and do some more examples like this. But let's look at one last piece here, and that's the hole in a rational function. And this is going to become even clearer as we do more graphing. But a hole in a rational function is created when the factored form of a rational function simplifies by canceling any common factors. The canceled denominator actually eliminates one of the vertical asymptotes, and it creates instead a hole. And this hole in the function tells us it's a point that doesn't exist, and we would just skip over it, just draw a little hole in the function. And again, this is going to become clearer when we start to graph. But let's first determine then any of these holes as well as any vertical and horizontal asymptotes. So the place to start with any function is it must first be factored. So we factor numerator, factor the denominator, and it must be fully factored. So let's go one step further, because in fully factored form, that difference of squares in the denominator becomes x plus 5 and x minus 5. Now, once it's in fully factored form, now we can determine different properties of this function. Well, first things first, let's try this new idea of finding any holes in the function. And the holes in the function are any values that would cancel out. Well, look at our function. The x and the x are going to cancel each other out. So this is the x equals 0 value actually cancels out. So there is a hole at x equals 0. We also have an x minus 5 canceling each other out. So we have a hole at x equals 5. There's the two holes in our function. Once we have the holes in the function, now we can take our function, and we can go back to the original, which is probably easier, and determine the vertical and horizontal asymptotes. So what I'd like you to do is pause the video and see if you can now find both the vertical and horizontal asymptotes. So the vertical asymptote, the only thing we have to do is make sure we simplify our function down, and we're left with 1 over x plus 5 minus 2, and that denominator would be 0 at x equals negative 5. That's the vertical asymptote. And for the horizontal asymptote, we divide everything in the original function, and we just have to do this in the rational piece. We don't have to do this to that number 2 outside here. We just have to divide everything in the rational function by x cubed, and then we can simplify this down, and this will allow us to find the horizontal asymptote. So we'll be left with 1 over x minus 5 over x squared over 1 minus 25 over x. Don't forget about that constant value, minus 2. Now we let x get really, really big, which means this will become 0, as well as that first term is 0, and this term is 0. And what we're left with is 0 over 1 minus 2. Now 0 over 1 exists, but we subtract 2 from it, and we just get negative 2. So our horizontal asymptote is at y equals negative 2. And we're going to do a lot of vertical, horizontal, and holes throughout this course.